Those stuff. Okay, so let's get started. What we've been doing so far is we've been talking about like the properties of distributions, and we kind of separated our discussion into properties of discrete distributions and properties of continuous distributions. They were similar, like parallel, but there were some slight differences. And so what I'd like to do now is to see if we can come up with some examples of some common probability distributions that we encounter in, say, a physics lab or something like that. And we're going to start with a discrete distribution. It's going to be the binomial distribution. And we'll actually end up using it to derive, or well, derive in quotation marks maybe, some of the continuous distributions, continuous probability distributions that we'll talk about. So this is an important example, and it's actually not particularly difficult to understand where it comes from. And so in fact, I think a lot of the stuff that we'll talk about today, you may have seen parts of it before, like maybe even in high school, some parts of it. So here's how we're going to start. This is useful when a result of an experiment, well, let's say the result of an experiment is only one of a small number of possible outcomes. So can be only one of a small number of outcomes. And so the standard examples are like rolling a die, flipping a coin, drawing a card. Okay, and what we're going to do is we're going to start with a specific example of flipping a coin, because that's an easy one to picture as we kind of develop some of the machinery that we're going to make use of. Okay, so if we toss n coins in the air, we can ask how many possible outcomes are there. So the idea is I've got like n coins in my hand. I just throw them all up in the air all at once. They hit the ground, they bounce around. And once they've all settled down, I just go look at them and I'm going to see which one is heads and which one is tails and so on. So let's see if we can enumerate the number of possible outcomes. So, you know, we threw them all up in the air. One of the coins is going to be the first one to land. And so that first coin that lands, there's two possible outcomes. It could be heads or it could be tails. Okay, so the first coin has two possible outcomes. Okay, and so what I'll do is I'm going to make a little table. So that first coin that hits the ground is a 0 or a 1. And so the number of possible outcomes is 2. Okay. And so then obviously the second coin also has 2 possible outcomes. And so what could happen is we could get a 0 or a 1 for that second coin. And we could get that 0 or a 1, whether the first coin was 0 or the first coin was 1. And so this would be a 0 or a 1. And so what we see then is that there's 4 possible outcomes after we looked at 2 coins. And we could write 4 as 2 to the power 2. Then the third coin hits the ground. We could have a 0, 0, and then a 0 or a 1, or a 0, 1, and then a 0 or a 1, 1, 0, 0 or a 1, or 1, 1, 0 or 1. And so we're going to end up with a total of 8 possible outcomes after we look at the third coin. And then you can see where this is going. Every time we add 1 coin to our handful that we toss up, we're going to increase the number of possible outcomes by 1 factor of 2, or 1 power of 2. Okay, and so we would keep going until we got 2 to the n possible outcomes. So for n coins, we have a total of 2 to the n outcomes. All right, that's easy enough. Now, what we could say is, we could ask the question, what's the probability that when we toss these coins up in the air, the first one that lands is a 0, then the second one is a 1, and the third one is a 1, and the fourth one is a 0. And so you just pick an exact kind of occurrence where you specify the outcome of every single coin. And we could say, what's the probability of that happening? If this is a fair coin, then whether we get a 1 or a 0 for any particular coin, it's 50-50 chance. And so there's no particular outcome that is more likely than any other, right? So if I want to select an outcome, I just follow this tree along any path. And so for 3 coins, 1 possible outcome is 0, 1, 0. That has the same probability of, say, the 1, 1, 1 path, right? So no path is special compared to another one. They all have the same probability. And so if there's 2 to the n possible outcomes, the probability of any particular outcome must be 1 over 2 to the n. And the reason that it might be the case is because if I was to ask, what's the probability of getting this first outcome, or the second outcome, or the third one, or the fourth one, or all of them, like when you do this or this, probabilities add. And so if I add up the probabilities of all the outcomes, it has to be 1. And if there's 2 to the n of them, I must be adding 1 over 2 to the n, 2 to the n times. Okay, if that makes sense. So the probability of each individual outcome are all equal to 1 over 2 to the n. Okay, I'll draw one more outcome. Like another outcome is we get 1, 1, and then 0. So there's all these possible outcomes. I could make 8 of these loops for the first 3 coins. Okay, fair enough. That means then that the probability of getting exactly, say, 1, 0, 1, 0, 0 for 5 coins is identical to the probability of getting 1, 1, 1, 1, 1. But if you actually did the experiment, if you took a handful of coins and 5 coins, threw them up in the air, they all hit the ground, and you got all heads, you'd be like, wow, that's amazing. I'm a genius. I got perfect all heads. But the likelihood of that outcome is no different than getting a 10100. It's just that the way that we interpret that kind of result is more like, oh, there was 2 tails and 3 heads. But there's lots of ways of getting that, right? If I say I want exactly the first coin to be heads, second one tail, third one heads, and then tail for 4 and 5, that's different than saying how many ways is there to get 2 heads and 3 tails. That's pretty common. But getting any exact sequence always has the exact same probability. It's a bit like when you look at the clock and you see that it's, I don't know, it's exactly 9:11, and you're like, oh, that's creepy. Whenever I look at the clock, I see 9:11. But it's not special. It's just that you associate that particular set of numbers with a major event, right? But it's no less like it's no more probable than you looking at the clock and saying, oh, it's 2:13. But I have no special association with 2 hours and 13 minutes. And so it's not special, it doesn't stand out, but it's just as likely as seeing 9:11 on the clock. Okay, so anyways, so for, whoops. So for, let's take n equals 5 points. The probability of getting, let's say, all zeros, maybe those are tails or something, is the same as the probability of getting exactly 0, 1, 1, 0, 0 in this order. And so just to be really explicit, this would be coin 1 has to be the tail, coin 2 has to be a head, coin 3 has to be a head, coin 4 a tail, coin 5 a tail. And you know, I could pick any sequence of 1s and 0s and the statement still is true. The difference is, however, is that there's lots of ways to make 2 heads and 3 tails. However, there are many ways of getting 2 heads and 3 tails. Okay, and I mean, it's easy to write down all those ways. We could get head, head, tail, tail, tail. We could get head, tail, tail, and you just keep going, and you could iterate through all the possible ways of getting 2 1s. Sorry, that would have to be a 0 here. Okay, I think that's that. And then we would have to have 0, 0, 1, 1, 0, 0, 0, 1, 0, 1. And then the last one would be 0, 0, 0, 1, 1. Okay, and there should be 10 of them. Did we get them all? 1, 2, 4, 5, 6, 7, 8. Right, 10 possibilities. All right. So what this tells us is that if I throw up 5 coins in the air, the probability of getting exactly this is the same as the probability of getting exactly all zeros. But the probability of getting 2 heads and 3 tails is 10 times more likely than us getting all exactly heads. So that's the difference. This actually has some relevance to, you know, if you take in your 3rd or 4th year, there's a course, Physics 403, statistical mechanics. And they think of, one way they think is, like, let's think of the air in this room. This room has a certain volume. What we could imagine is dividing this, let's call this room a cube. We divide it into a bunch of small little cubes, right? So maybe there's a million cubes this way and a million cubes that way and a million cubes vertically. And so we have a million cubes that fill up this room. And we could ask, well, how can we distribute all of the air particles in this room? And the answer is that it's most likely that we're going to have equal number of air particles distributed uniformly throughout this room. So we have approximately the same number of particles in every little cube that we divided the room into. One way to think of it is that there's actually equal probability of having the particles distributed in any way in the cubes in the room. So the probability of having all the air exactly in this cube is exactly the same as having one air particle distributed throughout this entire room. It's just that there's so many more ways of arranging the air particles so that they're distributed uniformly compared to the one way of putting all the particles in one little cube. So that kind of idea is similar to what we're talking about. Anyways, let's move on and see if we can develop this binomial distribution. So in general, if we toss n coins, we can ask how many ways or permutations. And so we're going to give some notation or some syntax of permutations, P, M, N, X. Okay, so we're going to ask how many ways can we get X heads out of N coins. So PM is just a shorthand for permutation, but we have N trials of an experiment, and we want to get X successful events where maybe tossing our coin is getting a head is a success. Okay, so how many permutations are there of X heads and N minus X tails when we do N trials? Okay, so one way to think about this is let's place all N coins in front of us, and then we're going to select one of those coins. If there's N of them, we can select any one of them, and we're going to say this coin is going to be, well, I'm going to change it so that it's definitely a head. And so when I make that selection, I can choose from all N coins, and so I have N choices to make. So step one is to select from our N coins in front of you and put one into our heads pile. Okay, so we have N possible choices. All right, and then in step two is we're going to select a second coin. We're going to have N minus one left to choose from, and we're going to put that in the heads pile. Okay, so step two is to select from the N minus one coins and add one to the heads pile. So there would be N minus one choices. Oops. All right, so now I have two coins in the heads pile. If I want to get up to X coins in the heads pile, when I make that choice, I will have how many coins left to choose from. So I previously chose X minus one. So I would have N minus X minus one coins left to choose from. So we're going to keep going. We'll get up to step X, and we're going to select from the n minus x minus 1 coins remaining. And we add 1 into the heads pile. And so this is n minus x plus 1 if we bring this minus sign in. And so that's how many we can choose from in this case. All right, so then the total number of permutations is, okay, it's going to be PM nx is going to be, well, we first had n choices, then we had n minus 1, then we didn't write it down, but we would have n minus 2, and then we would go to n minus x plus 2, and then we would get to n minus x plus 1, and then after we made that last choice, we would have our x coins in the head pile, and we would be finished. Sorry, I need my plus 1 in there. Plus 1. Okay. Can anybody think of like what's a more convenient way to express this? Factorials? Yeah, factorials. So what I'm going to do is I'm going to put an n factorial here. What do I have to do to make this, like this doesn't go down to 1, right? It stops at some place. So what should I do? Yes, that's right. Exactly. Okay, and so this is the number of permutations. And so let's do our example. N equals 5 and x equals 2. We drew all those possibilities and we saw that there was 10 of them, right? So let's check this out. So the number of permutations is going to be 5 factorial divided by 3 factorial, which is 5 times 4. It's 20. All right. So can anybody think of why did we calculate 20 here, but we drew only 10 possibilities? Yeah, there's a factor of 2. What's the factor of 2? Where does it come from?
You could like mirror all of them. So like the 1 1 0 0 0 could go 0 0 1 1 1. And just like if you
so we did like this. These are the mirrored ones are there already.
I think take rid of the word for the same 1 1. It's also counting.
Yeah, that's right. Okay, I think you got it. So like if I took the first point and I said you have to be ahead, and I said, and then I took the second point and said you have to be ahead, I could have chose coin 1 first and coin 2 second, or I could have chose coin 2 first and coin 1 second. And so I'd have 2 outcomes that look like this that are actually distinct orderings of how I chose the coins. That's what it is, exactly. Okay, so I want to try to express that in words that aren't too complicated. So the question is, why is PM 5 2 equal to 20 different than the 10 possibilities we drew? Whoops. Okay, so let's consider just the first one that we drew. Consider the 1 1 0 0 0 outcome. Okay, so the number of permutations considers that the order that we make the choices of our heads matters. So if we choose this one first or this one first, are distinct possibilities, even though the outcome looks the same.
zeros on that?
No, so in the binomial distribution, what we're doing is we're selecting X from N objects. And so it's how we select the X that matters. Okay, so in other words, choosing coin 1 first or second is distinct. Okay, it turns out that if we have X heads, there are X factorial ways to order them in our heads pile. And so let's see that. And X equals 2 is not a good example, but that's the one we'll start with, and then we'll look at another one. So example, X equals 2, we could have, whoops, we choose our two heads, which we signify as 1, and we could choose them in these two orders. And X factorial equals 2 factorial is just equal to 2. The reason I said this one's not a good example because 2 factorial is just 2. So it doesn't illustrate the point. But if we had X equals 3 heads, for example, then we could choose them. And so let's see if we can get the ordering right. So we're going to go through some permutations of how we cycle the 1, 2, 3. So I'm just going to shift everything to the right. 1, 2, 3. And then we have to do it in the reverse order, 3, 2, 1, or 3, 2, 1, or 3, 2, 1. And so these are all the different ways of ordering 3 selections, and there's 6 of them. And 3 factorial is 3 times 2 times 1, which is 6. Okay, and then if you had 4, it would be 6. So there would be 24 ways of ordering 4 objects. Okay, so it's usually not the number of permutations that we're that interested in. So they have a different terminology for the number of permutations when the order of how you select X doesn't matter is called the number of combinations. Okay, so the number of combinations, which we're going to denote C of NX, of X heads from N coins when the order of X doesn't matter, is C and X is going to be the number of permutations, which we've already worked out, divide by this X factorial to factor out the different ordering of the X values. And so the number of permutations was N factorial divided by, well, it was N minus X factorial. And so now we're going to have that additional factor of X factorial. And so this you probably have seen before as the number of combinations. Does anyone remember, like, there's some fancy terminology for this. How do people say it? Yeah, N choose X. And so this is often, so this N factorial over X factorial, N minus X factorial is often read as N choose X. And it's also often given this kind of funny notation. You've probably seen this thing before. Yeah.
Isn't it called a binomial?
Yeah, that's what we're doing. We're almost there. So this is going to be, we're going to write down a probability for getting X successes out of N trials. And this thing is going to be the prefactor in our probability. Yeah. And so this is the N choose X. It's, you know, there's no division sign here. Like that's the only thing that you have to remember. Oh, okay. Sorry, go ahead.
So this, we said at the beginning that this is really only true for small choices or small possible outcomes. So is there like an upper bound to what X can be?
No, I mean, by the number of outcomes, what I mean is you do one experiment and the result can only be one of a small number of events. So in our case of flipping a coin, the small number of outcomes is the heads or the tails. So X and N can be arbitrarily large. It's just that when you do the experiment, there's only a couple of possible results for that experiment. Yeah. Okay, so let's just confirm our example for X equals 2 and N equals 5. So N equals 5, X equals 2. We want to get a 10. And so that's going to be 5 choose 2 is going to be 5 factorial divided by 2 factorial divided by 5 minus 2 factorial, which is 5 times 4 divided by 2. So this is going to be 3 factorial. So we divide out the 3 times 2 times 1. And then 2 factorial is just 2 times 1. And so this indeed is the 10 that we were expecting to get. All right. So we're now going to do the probability. And we're going to actually write down this binomial distribution. Okay, so probability. So since each outcome has the same probability, and we wrote that down at the beginning, 1 over 2 to the n, right? We toss up 5 coins, watch them hit the ground, and there's 2 to the power of 5 possible ways they could land. So 2, 4, 6, 2, 4, 8, 16, 32 ways they could land. Okay, has the same probability of occurring. The probability of getting X heads from N coins is. All right, so now this is maybe a more interesting question. You know, we said I throw up my coins and then the probability of getting exactly 1, then 0, then 1, then 0, then 0 is no different than getting all zeros, for example. But if I ask the question, what's the probability that I throw up 5 coins and 2 of them lands heads? Well, I say, I'm going to take the probability of any particular outcome, and then I just have to multiply by the number of combinations that have 2 heads out of my 5 trials. And so that's just the N choose X. And so this probability is going to be equal to N choose X times 1 over 2 to the N, which is the same as N factorial over X factorial N minus X factorial 1 over 2 to the N. And so this is the number of combinations. And this is the probability of any particular outcome. Okay, So we're getting pretty close to where we want to be, but so far, this result is only valid when the probability of getting X from a single trial is 1/2, right? Because that 1/2 is right here. It's 1/2 to the power n. But we could have scenarios where we say, all right, what is the probability of, I don't know, flipping this coin where the coin has a 75% chance of landing heads and only a 25% chance of landing tails. So there could be other scenarios, right, where we roll 50 die or 50 dice and we say, well, what's the probability of getting, I don't know, seven times that we get a 1 when we roll the dice 50 times. Well, then the probability of getting a 1 is not 1/2, it's 1/6. So we want to generalize this. So this is valid only when the probability of getting results X, like for example, heads in any single trial is 1/2. All right. So in the binomial distribution, generally what we'll talk about is things like what is the probability of success or failure in a single trial of a measurement? And so what we're going to require is that when we sum success and failure, we want to get a 1. So for example, if it is flipping a coin where probability of heads and tails is equal, then we would say probability of getting the success is 1/2. The probability of failure is 1/2. They total 1. What's the probability of rolling a 1 when I throw 1 die? Well, probability of success is 1/6, and then the probability of failure will be 5/6. Okay, and so they have to add up to 1. All right, so in general, the probability of the possible outcomes could be different. So example is a weighted coin. So if P heads is equal to P, so this is probability of getting heads, and the probability of getting, let's say, tails is P tails. People usually use Q, so they usually use Q and P for binomial distribution, where P is the probability of success, like that's the desired outcome, getting heads or something like that. And then Q is the probability of failure, getting the not desired outcome. So this is probability of, let's say, a successful event. And this is going to be the probability of a failed event, a failure. Okay. So then what we could do is we could say the type of question we were asking with our binomial distribution is, what is the probability of getting X successes out of N trials? Well, if I was flipping a coin and I wanted, and let's say it's a weighted coin, and I wanted 2 heads, then I would say, well, the probability of getting 2 heads and 3 tails is P times P squared, times Q times Q times Q cubed, right? So remember probabilities, if you say, what is the probability of getting X or Y, you would take the probability of X plus the probability of Y. If you were to say, what's the probability of getting X and Y, you would have to take the product of the probability of getting X times the probability of getting Y. So here we're asking, what is the probability of getting heads, and then tails, and then tails, and then tails, and then tails, and then it's going to be P times Q times Q times Q. Okay. So if all of this is true, then the probability of X heads and N minus X tails is P to the X times 1, well, I guess I'll write it as P to the X times Q to the N minus X, which people will often write as P to the X times 1 minus P to the N minus X, where P plus Q must equal 1. Right, so from one trial, you must get a success or a failure. So those probabilities have to add up to 1. All right, and so this is going to be true for any ordering of the heads, right? Whether you want the first two to be heads or some weird, like the first one and the third one or whatever, they all have that same probability. Okay, so then this is enough to get us to our binomial distribution. So therefore, the binomial probability distribution is, okay, so we're gonna denote it PB for binomial, and what we want is X successes out of N trials when the probability of a successful trial is little p. So let's just label all these things.
So what does a semicolon mean?
I don't know, it's just how it was written down in a book. It just means that the X is the important thing, so this is how many successes we want. Whether you put semicolon or just a comma, but to me it doesn't matter. But this is going to be the number of successful outcomes, this is going to be the number of trials, and this is going to be the probability that any single trial is successful. So this is, X is the number of successes, N is the number of trials, and P is the probability of any single trial being successful. Okay, and so what this is going to be equal to is it's going to have our prefactor of N choose X, and then it's going to have the probability of getting X successes and N minus X failures. And so often you'll see this written as N choose X, we can expand out N factorial over X factorial, N minus X factorial, and then P to the X, and then often they will write Q as 1 minus P, N minus X, and that's our binomial distribution. Okay, so we have a few minutes left. Just looking ahead, one thing we're going to try to do is we're going to try to see if we can write down the mean and standard deviation of the binomial distribution. So what we're going to do is we're going to use the stuff that we worked out for discrete distributions. So next time, find the mean and standard deviation of the binomial distribution. Okay, so if you remember, what we said is that the mean was going to be equal to, what was it? Who remembers? What did we have to do? Yeah, that's right, exactly. Xj, P of Xj, and then we had to sum over all of the possible outcomes, right? And so that's what we're going to end up doing. And so we're going to take, for this probability, we'll put in the binomial distribution here, and then we're going to try to evaluate the sum and see if we could work out the mean. When we do the standard deviation, what we're going to try to do is we're going to try to evaluate. So remember sigma squared, we had a neat way of writing this, right? We wrote it as the average of x squared minus the average of x squared. And so this is going to be mu squared. So if we do the calculation for mu, then we'll know this result. So this is going to be mu squared, and this x squared will be the sum over j of xj squared p of xj. And so these are the kinds of calculations that we'll try to do on Wednesday. So that, I think that's where I want to stop. I don't want to start that now because we won't get very far with it. Okay, so have a good weekend, and we'll see you. Well, we'll see some of you on Tuesday, some of you on Wednesday. All right. And so just remember, when you come to the lab next week, you will hand in two things. You're going to submit your lab notebook for experiment number 1, and you'll submit your pre-lab for experiment number 2. And then you also have to have your second lab book so that you can use it for your experiment number 2 notes. All right, good. Thank you.
So a quick question.
Yeah.
Our lab, the root cause experiment.
Yeah.
For the first part, we could take the mass of the ball that we